Assalamu alaikum. I hope all of you will be quite fine. In this video, I will be explaining the method for the solution of the velocity analysis using instant center technique for the example that is available in chapter number 6, but its graphical position analysis is given in chapter number 4. Position analysis is given in chapter number 4 in example 4-2, but the same example is repeated in chapter number 6, which I will later be showing in this video. That example actually requires the velocity analysis. So to save time, I am just copy pasting this example in Microsoft Word, and further I will be explaining the procedure to determine its instant centers both for this right circuit and this left circuit 1 and circuit 2, which are mentioned here, open and cross circuits. So I can first of all take the snapshot of this complete diagram position solution for this example 4-2, and I can just, for example, copy it on some blank page. Here, for example, I have pasted the diagram just to save time and to avoid drawing it freshly. But to draw such diagrams on Microsoft Word, I have explained the procedure in several other videos, so you can consult them. They are available on YouTube. So this example actually shows the position analysis and necessary required angle, and we are familiar that before any velocity analysis we must perform or know its position analysis or positions of necessary links. For example, for the case of crank dash slider mechanism, because crank is the input and slider has two possible positions. Slider, because slider is the output, and that has two possible locations or positions, one on the right or one on the left. And again, we know, we can observe in this video that the offset is towards the negative orientation, because conventionally the origin of coordinate system, global coordinate system, is always selected or placed at O2, which is the crank grounded revolute, and if the slider, if the offset is positive, then the slider will be either in the first quadrant or in the second quadrant, because in both of those cases the offset or the y-axis, because the positive offset will be toward the positive y-axis along in the direction of positive y-axis. So the sliders will be placed either in the first quadrant or in the second, but if the offset is negative, then the slider will be placed either in the third quadrant or in the fourth quadrant. So at this time this slider is in the fourth quadrant and this slider is in the third quadrant. So this is just an explanation for the position analysis. So the data is given here for the position analysis, and now we can move to chapter number 6. The same example has been repeated there. So here this example 6-8, the same example that was 4-2 example, that has been repeated here as for the velocity analysis. So the statement of the example is written here: given a 4-bar crank test slider linkage with the link lengths L2, which is link number 2 or the input link, and its scalar length is A 40 mm. L3 is the link always in complex motion for the case of 4-bar mechanism, and its scalar length is denoted by letter B 120 mm. Offset is denoted by small letter C, which is actually, we can say that it is actually the perpendicular rocker to the offset slider axis here. Sorry, the diagram is not available here at the moment. I think yes, this is available here in figure 6-21. The same diagram is also available in chapter number 4. So this is actually the C, which is the actually slider offset. So in this diagram it is in the first quadrant, but in the example, because the offset is negative, this slider is located in the fourth quadrant. So that is the case. As we can observe here, C is minus 20 mm and the input is same, theta to 60 degree and omega to minus 30 radian per second, means minus sign actually represents that the angular velocity for the link 2 or crank is in the clockwise orientation or direction. So that require that find the omega 3, means the angular velocity of the link which is in complex motion, and the linear velocities of points A and B for the open circuit. So linear velocities for the point A and B That means point A is actually the crank moving revolute and B is actually the slider point where slider is located. So that says use the angles and positions found on the same linkage and its link to position in the example 4-2 which I have previously referenced it. So according to the example 4-2, the angle theta 3 and the slider position D for the right circuit is shown for this circuit, as we can observe, shown in red color on the right direction from this global y-axis. So first of all, we can find the instant centers for this link for the right circuit. So in order to determine the instant centers using the linear graph technique, so what we can do, as we can observe here, that here are actually 4 links, means crank and connecting rod and slider, and the fourth one is the ground actually, which is usually denoted as the link number 1. So there are 4 links. So to save time, I can copy the linear graph from some previously drawn diagram. For example, I can copy this linear graph from here. Complete linear graph can be copied and paste it there just to save time. So labels can also be copied from there. One label can be copied at one time, so copy it and paste it anywhere and then reposition it. Here, for example, just change it. This is 1, and again, for example, we can just copy paste it. This is 2, and again paste it and change it to 3, and again paste it. Sorry, this is 4. So To make our work more easier, uh, we can create two separate linear graphs for the unknown instant centers 1 comma 3 and 2 comma 4. So I have created these two separate linear graph. This linear graph is actually for the connection for the instant center for the links 1 and 3, and this linear graph is for the link number 2 and link number 4, and both of these linear graphs are for unknown instant centers. So first denote the known instant center using the common nomenclature that can also be copied from another diagram which has already been defined here. For example, this is instant center 1 comma 2. So just right click on it and send it to for example behind text, so that text can be easily pasted here. So actually this is instant center 1 comma 2. This crank grounded revolute because this is link number 2 and this whole ground is actually link number 1. So this is the permanent instant center I1 comma 2. So simply just copy and label the other instant centers as explained while in the class, that this is instant center permanent instant center because this is link number 2 and this is link number 3 or the connecting rod which is in complex motion. So change this to this is link number 2 and this is link number 3 orderly. So this is instant center 2 and 3 and similarly this link number slider is actually the link number 4, which is actually I will be explaining a bit later. This is link number 4 and this is link number 3rd. So label its instance center as to be, this is link number 3rd and this is link number 4. So this pin, the pin at B is actually the instant center 3, 4, because slider is link number 4 and this connecting rod is actually link number 3rd. So the 4th permanent instant center will be located. So for the location of the 4th permanent instant center here, because this is instant center between link 1 and 2 will be, permanent instant center will be 1, 2, and between link number 2 and link number 3rd the instant center will be 2, 3, which has been located. And similarly the instant center between link number 3rd and link number 4th has also been determined, but now the permanent instant center between link number 4 and 1 or 1 and 4 is still to be determined. And we are familiar that in for the case of slider, because apparently there is no full revolute joint between this slider and this ground. So actually, as the author has mentioned in the book of design of machinery in articles, that this slider B, it is actually equivalent to an infinitely long rocker link, which I can show here for just for your further study and as a reference. Here in this figure 6-6, where the non-offset slider crank chain has been shown here. Here as we can observe that this point is actually the permanent center I3, 4, and here the author has shown that the effective link number 4 means the rocker link is actually, this is infinitely long rocker link and its grounded pivot is actually at infinity, effective rocker pivot O4, which is at infinity. So this is the permanent instant center I1, 4 is located at infinity. So its equivalent the author has shown here. So in the next figure 6-7, where the author has shown the general case, here we can also observe that this point, this revolute, which is actually between the slider and the connecting rod, this is instant center 3, 4, and the fourth permanent center, which is actually the effective rocker, is actually perpendicular to the slider axis, and its grounded revolute joint, which is actually the permanent instant center between the ground and the fourth link, which is actually the infinitely long rocker or this slider. In this case, its instant center is I1, 4. So in this way, so this is the method. So now proceed to the same example 6-8 and the figure which I pasted here. So that means the permanent instant center, in a similar manner I can just draw here infinitely long rocker just for your reference, like the author has drawn. And just copy this label and paste it here, for example. This is 1, 4, and I can also insert here the infinity symbol. Here like this, just to make you understand. So this is the effective rocker link 4, and this is actually the whole surface is actually the ground. So this is the instant center. So all 4 instant center have been shown here. Now the problem remains for the unknown instant centers. So as we can observe, now we will be determining the instant center for the link number. For example, in the first stage for link number 1 and link number 3rd. So as we can observe that link number 1 and 3rd are not directly connected, because between them is link number 2. Between them is link number 2 and the link number 4 are the slider. So link number 1 and 3rd are not directly connected, because between them is link number 2 crank and the link number 4 slider. So in order to determine their instant center, what we will be doing, that we will be using the Kennedy's theorem. So Kennedy theorem actually states that the 3rd instant center will be located on the line connecting the two permanent instant centers which have been previously found out. So this is the statement in my own words, just for explanation. The actual statement is different, that is written there. So as we can observe here, that between link number 1 and link number 2, we will be considering first this right triangle. So permanent instant center 1 comma 2 and permanent instant center 2 comma 3. The line which will be connecting the permanent instant center 1 comma 2 and the permanent instant center 2 comma 3, that line will be extended in both orientations. So the 3rd permanent instant center will be located on that line. So I can draw the line here. For example, this is permanent center 1 2 and this is permanent instant center 2 comma 3. So I can, for example, draw here the line. So here, so again make it as the just reference line, make it in some dashed pattern. So the 3rd permanent instant center third permanent instant center will be located on this line. So in order to determine the exact location, we will be using this other trio, this left triangle of this linear graph. So as we can observe here, that the unknown instant center link I1 comma 3 will be located on the line connecting the permanent instant center I1 comma 4 and I3 comma 4. So as we can observe here that this is I1 comma 4 and this is I 3 comma 4. So as we can observe, when we proceed this line in either direction, so that line will be intersecting this line here in this location. So I can just, for example, extend this line instead of drawing another line. I can just use this line. So in this way, for example, I can copy just this label here. So this is the instant center I1 comma 3, means this is the instant center for this link number 3rd and this link number 1, which is the grounded link. So instant center, this instant center has been found out, and just further for better labeling it, use a small circle just to represent clearly the permanent instant this unknown instant center. This instant center is actually changing at each and every instant depending upon the motion of these links. So this permanent center. So now we will be using this other linear graph to locate the instant center, which is actually connects the link number 2 and link number 4. So the 6th instant center will be located. So first of all, for example, use the lower triangle, for example, for the first time, because this permanent center have been easily located. So as we can observe, the unknown instant center I2 comma 4 will be located on the line connecting the permanent instant center link of link number 2 and 3rd, which is I2 comma 3, and the line connecting the permanent center for link number 3rd and link number 4th. So here, as we can observe that this is permanent link number 2 comma 3 and this is permanent center 3 comma 4. So that means we can draw insert a line and extend it in the both directions like this. Just extend it in the both directions so that the instance center will be located where the intersection will be available. So make it in also dashed pattern. Now as we can observe here, we will be using the upper triangle for example. Actually the triangles, these tries can be used in any order, but I have used the lower trio first just to make you understand the concept which I am stating here. That now we can observe that the exact location of the instance center 2 comma 4 will be located by using this trio upper triangle, which is actually on the line which is connecting the permanent instance center 1 comma 2 and 1 comma 4. But as we can observe here in the diagram that this is the permanent instance center 1 comma 2 and this is the permanent instance center 1 comma 4. But as we observe that this instance center 1 comma 4 and 1 comma 2, because this permanent center is actually located at infinity, so that means they cannot be connected directly, because here that is just shown for as a reference, but infinity cannot be located on the paper. So that means we will be using the concept that we will be drawing a line parallel to this effective rocker link through O2. We will be drawing a parallel line to this effective rocker link, and that parallel line will be passing through this permanent instance center I1 comma 2, and those parallel lines, as we are familiar from the geometry, that parallel lines do intersect at infinity. So at infinity this instance center I1 comma 4 and this permanent instance center will be on a common line. So that means we will be drawing a line parallel. For example, I can just copy it and just can, for example, move it, or I can freshly draw it here like this. So as we can observe that at infinity this instant center I1 comma 4 at this instant center I1 comma 2 of this upper trio will be located on the same line, and that means because this line is actually not intersecting this instant center, because that is actually located where the permanent center I3 comma 4 is located. So here the intersection is possible. So this is the instant center I1 comma 2 comma 4. So I can, for example, just copy this label, and also I can, for example, copy this mark as well. So sorry, I can just copy label first and paste it at some suitable location, and then move it here, and then, for example, change it to 2 comma 4, and again just, for example, copy this mark as well. So in this way, this is the instant center 2 comma 4 that has been located. So once the instant centers have been located I1 comma 3 and 2 comma 4, so all the 6 instant center for this 4 bar crank dash slider chain have been located. So now the task is that we will be determining or solving the triangle A I1 comma 3 B, because that triangle actually consists of this connecting rod or the link in complex motion. So I can just, for example, I can state here that the triangle A I1 comma 3 and B. So as this diagram has just been copy pasted, so to solve it graphically, I can suggest first of all we will have to define some scale for the for length. So for example, I can use this linear scale here. in this view, because this diagram is actually just has been copy pasted. So first of all, in this view I will be determining the scale. So I am estimating the scale just. So for example, as we can observe here, the distance between this line and this line is 126.84. so I will be determining that how much 1 centimeter will be equal to. So I can observe here that, as we can show, that this distance of 126.84, or for example I can send it to back, or send it to wrap text behind text like this. So sorry, because this is the picture, so again send it to back. So here we can note that distance here in this view, which is equal to 8.6, so it is equal to 8.6 centimeter. So that means 126.84 is equal to 8.6 centimeter, or I can use calculator here. Here and 126.84, so that means one 26.84. So that means in this view I will be dividing that 1 centimeter is equal to how many millimeters, or I can say 10 millimeter is equal to how many millimeters. So that means that 126.84 will be divided by 8.6 here, sorry, here, as you can observe that this 8.6 centimeter distance was equal to 126.84 millimeter. So that means this 126.84 will be divided on this 8.6 centimeter. So that means 1 centimeter is equal to 14.748 millimeter, for example. So just for the graphical purpose I can just approximate it to one decimal, for example 14.7 centimeter. So 14.7 millimeter. So 1 centimeter here I can say, I can mention here the scale on the next page. For example, 1 centimeter is equal to 14.7 millimeter approximately in this view. So because this instant center have been located in this view, so now I will be measuring the distances in this triangle A I1, 3. So that will be equal to, according to this view, so here I can observe that here 4 centimeter, 14 centimeter, 14.1, 14.2 or 14.3, so that is equal to 14.3 centimeter. So that means here we can convert that 14.3 centimeter and 1 centimeter here in the scale was equal to 14.7 millimeter. So that means we will be multiplying it by 14.7. So that means that is equal to 210.21 millimeter approximately. So I can mention here that I1, 3 is equal to 210.21 millimeter. Remember, this is the just approximation. And again observe, measure BI1, 3 means the distance from point B to this instant center. So just change it here and now determine it here using this linear scale again, and now move it exactly vertical and place it here. Like this. So as we can observe here that up to here 15 centimeter have been completed. So just draw here a reference line, because scale cannot be resized. So now here move, and now observe that here the distance is, this is up to here approximately 1 centimeter, approximately 1 centimeter I can say. So that means 15 or 16 millimeter approximately, because up to here was 15 centimeter, so 1 centimeter above. So that means bi 1 comma 3 is equal to, according to scale, that is equal to 15 centimeter, and 1 centimeter is equal to 14.7 according to scale. And so this comes out to be 15 multiplied by 14.7, so that is equal to 220.5 centimeter approximately. So 220.5 millimeter. So in this way the distances ai 1 comma 3 and bi 1 comma 3 have been located. And now if according to the problem statement here in this example, that omega 3 is equal to omega 2 is equal to minus 30 radians, so we will be determining the magnitude of the velocity va. So that magnitude can be very easily determined, that v subscript a, just change it to subscript, v subscript a is equal to, as we can observe, that is equal to O to A and multiplied by omega 2. So which is equal to O to A is 40 millimeter, as that can be observed here, and O2 is 30 radians per second. Just use its magnitude because we are to require the magnitude just. So that comes out to be 1200 millimeter per second. So its direction that can be shown here with the help of this arrow, because it is in the clockwise direction, and that must be in every case perpendicular, because this is 60. So that means the velocity angle along with the horizontal, as I can show here, just I can make it a reference line here, just here, just make here the imaginary reference. As we can observe that the angle of the crank with horizontal is 60 degree, so this alternate angle will also be 60 degree. So as the velocity is actually perpendicular to this link, so that means this will also be 90 degree, this angle will be 90 degree, the angle of the velocity with this crank will be 90 degree. So that means this is 60, so that means this is 30. So the angle of the velocity with the horizontal is 30 degree, so this angle is 30 degree. So that means the direction of this velocity is 30 degree along the horizontal, and this velocity vector is in the fourth quadrant, as we can observe, the angular velocity is in the clockwise orientation. So now we can observe that actually this velocity is determined with the help of this crank. So now we temporarily shift this point to on the link in complex motion, which is link number 3rd, AB. So now AB is actually in pure rotation about this instant center I1 comma 3. So that means the velocity, this velocity is actually, as we can observe here, the center of rotation for this velocity for the common point on the link AB. This velocity is actually rotating this connecting rod in the anti-clockwise orientation, as we can observe here, or if we can draw some arrow here, if I can find some suitable arrow, so I can show it here, that the rotation will be like this. So this, in this way, because this velocity will be rotating this radius, so this will be the radius of rotation for the connecting rod. So this velocity will be rotating this radius AI1 comma 3 in the anti-clockwise orientation. So this direction is anti-clockwise. So that means the direction of rotation of the connecting rod is counterclockwise, or angular velocity omega 3 is positive, but the crank input velocity, angular velocity, is clockwise, which is negative. So in this way, and now the magnitude angular velocity, the magnitude of the angular velocity will be obtained by dividing the magnitude of this velocity of VA on the radius to the radius AI1 comma 3. So the distance from point A up to the instant center I1 comma 3, because this is the radius of pure rotation for the link in complex motion, because this link has been mapped into pure rotation about this instant center I1 comma 3. So now we can find it here, that omega 3, I can write it here, which is actually the angular velocity for the link in complex motion, which is actually the connecting rod AB. So this velocity will be equal to VA divided by this AI13 and which is equal to 1200 divided by so this is equal to 1200 divided by 210.21 210.21. So this comes out to be 5.7085. so that means the angular velocity is 5.7085 radian per second. So as we can observe here that the author has uh, calculated the omega 3 5.616 radian. So our answer is 5.7, which is very nearly equal, because these are the graphical results and they are quite okay. So that means our answer is 100% correct and the angular velocity has been satisfied. After that, the requirement is the linear velocity of the slider. So that means we will be calculating the velocity of this point B on the link in complex motion, and the absolute velocity of this point B which is located on the complex link AB, which is the connecting rod. So once the absolute velocity for this point B has been calculated using this instant center I1 comma 3, then this point will be shifted on to the slider because that is the common point, and after that that will be giving the velocity of the slider. So that means here we can just copy, for example, just copy it here. So sorry, just copy it here. So change it to VB, and this is actually equal to O. So VB will be equal to B I3. I can just copy from here and multiplied by omega 3, because the velocity is equal to R omega, and for point B the R is equal to B up to I1 comma 3, this distance which has been calculated here, and the omega 3 is already have been calculated as above. So here I can write here that BI 1 comma 3 is equal to 220.5. just copy it from here and paste it here, and the omega 3 has been calculated as above. So just copy paste it here, and now calculate here that 220.5 multiplied by 220.5 multiplied by 5.7085. So multiplied by 5.7085. So this comes out to be 1258.72 millimeter per second. So just copy from here and just paste it here. So as we can observe that this is the velocity of the slider. So now from the book we can say that the author has calculated the result for this right position of the slider to be 1346, and our answer is 1258. So our results are quite near, because these are the graphical results and these are actually the analytical results, so they are quite near. So that isn't an issue, and our results are very accurate. So in this way, now the other method is that we can also calculate these magnitudes ai1 comma 3 and bi1 comma 3 trigonometrically. So to calculate the trigonometric, so we can observe here that this angle, for example, this from this horizontal up to this connecting rod is 152.91. so that means this angle will be equal to 152.91 minus 90 degree, because this quadrant is actually between vertical and horizontal is 90 degree. So I can just copy some angle symbol from anywhere. Just I can copy it just to save time. So I can first of all will be solving the angles, all the angles will the in the triangle a I1 comma 3 and b will be determined. So sorry, here at any suitable location just paste, and now move this so here this angle will be equal to, I can just copy some label from some other diagram here. For example, I can just copy label from here or some other better diagram here. For example, suppose I can just copy it from here any label and just modify it. Just paste it anywhere. So move it here. So this is equal to, this will be equal to 152.91 minus 90 degrees. So that comes out to be, just resize it. So here as we can observe that 152.91 minus 90 degree, so this comes out to be 62.91. so this comes out to be 62.91 degrees. So in this way, and this angle between this connecting rod and this line ai1 comma 3, as we can observe here that the angle for this straight line is actually 180 degree, as we know from the geometry. So angle up to here is 152.91. so that means this angle, this smaller or acute angle here between this connecting rod and this x-axis, this angle will be equal to 180 minus 152.91. so that angle will be equal to, as it can be calculated here simply, that 152.91 which is equal to 27.09. so that means here this angle will be 27.09. so that means the angle between this horizontal line and this connecting rod, and remember this this velocity has angle with the horizontal exactly 30 degree, so that is somewhat below here, and this connecting rod is above because the angle between this horizontal line and this connecting rod is the alternate angle for this angle, and this angle is 27.09. so this total angle will be equal to 60 degree. This is the 60 degree because this is the alternate angle for this 60 degree, and so this is also 60 degree up to this horizontal and this line. 60 plus 27.09, so I can just add it here, 60 degrees, so this comes out to be 87.09. so I can, for example, just copy some or I can freshly draw just an arc just to show the angle symbol here. Sorry, just undo it, insert, go to shapes and click on this curve here. So as we can observe it here, or so this angle I can just copy this label from here and paste it here and move it here, that this angle is actually equal to 60 plus 27.09, which is equal to 62 point here 87.09 degrees. So that means this angle has also been calculated. So the third angle is now quite easier because this angle will be equal to the 180 minus the sum of this angle and this angle. So I can just add these two angles, which is equal to other angle is 62.91. So this is 150. So that means this third angle will be equal to, for example, 30 degree just. So that angle will be equal to just 30 degree. So just copy this label from here and paste it here and change it to just 30 degrees just for reference. So as we can observe that all angles have been found out. So after that we will be applying the law of sines on this triangle AI 1, 3 and B. So on this triangle we will be applying the law of sines, so that can also be applied here, that law of signs that can be applied here. So just as a representation, so I can mention here that ai1 comma 3 divided by sine of because the angle in front of ai1 comma 3 on this side is this angle 62.91. so I can just directly input the angle here. The angle is 62.91. in a similar manner, just for example, just copy it here and paste it here and change it to bi1 comma I comma 3, and the angle in front of this side is actually 87.09. so just change the angle to be 87.09. so 87.09, sorry, 87.09, and again just paste it here and change this to AB, which is actually this connecting rod itself. so the angle in front of it is 30 degree, so just change it to 30. so in this way now for example, I can calculate here similarly as it was calculated here, that ai1 comma 3 will be equal to, actually compare these two terms with this third term. so as we can observe, ai1 3 will be equal to AB multiplied by sine of 62.91 divided by sine 30. so just calculate it here, that AB, which is actually the connecting rod length, and that is actually the letter scalar length B, which is 120 millimeter. so AB is 120 millimeter. so just I can calculate it here, just clear the history. so as we can observe here that AB is 120 millimeter, and just multiply it by sine, sorry, 120 multiply, sorry, again 120 degree, and multiply it by the multiplied by sine of 62.91. so multiplied by it 62.91 and its sine. so sorry, I think this is in radian, so actually change it into degrees. Once again calculate that 120 degree multiplied by 62.91 and its sine, and this comes out and this comes out to be 106.83. so as we can observe here that the analytical result here is 106.835. so 106.835. so our graphical result was 210.21 millimeter. so let us see it once again. I still to divide it by sine 30, so that was not divided, so just divide it by sine 30 and as we can observe here, this is 213.67. so here just write that is 213.67 millimeter. so here our results were 210.21. these were the graphical values, and this is 213.67. this is the analytical results. so that means our graphical results were quite near and they were quite okay. so AI3 has been calculated, and again in a similar manner, if at this stage we can just calculate omega 3 from this analytical formula, so I can just paste it here, and now I can just paste this value here instead of the graphical value here, and now I can calculate the new value here, for example 1200 millimeter per second divided by this value 213.67 and divided by 213.67. so as we can observe here, this is 5.616, and as we can observe here, the answer is 5.616 radian per second. so hence our analytical results are 100% accurate and correct. so in this way the trigonometric value of omega 3 has been calculated. And again in a similar manner, now calculate bi1, 3 analytically. so bi1 will be equal to AB multiplied by sine of 87.09 divided by sine 30 just. so just copy it here, bi1, 3 will be equal to bi1, 3 will be equal to, again in a similar manner I can just calculate it here, that is 120 multiplied by sine of 87.09. so 87.09 and its sine, and this will be equal to 119.84, and just divide it by sine of 30 degree. So sorry, just as we can observe here that this comes out to be 239.69. so just copy paste from here, that is equal to 239.69, that is sufficient. So just paste it here, 239.69 millimeter. So BI3 analytical value is 239.69 and our graphical value was 220.5 millimeter. So that is very nearly equal. So now calculate VB from the same formula. Just copy paste it this value here and change it. Now as we can observe that here just copy this value and again here the omega 3 value must be I can just make it here the heading that this is graphical and these are all graphical results, and from here are trigonometric or analytical results. So here actually this value is has not been changed because actually sorry so this value was actually 5.616, actually that I did not paste here, so that was 5.616. This was the analytical result as it was shown here. So radians per second. So use this analytical value here, must be used analytical values, because in the analytical formula or the analytical results will be input. So now just for example I can just copy it from here and for example clear this all history and just paste it here. So enter, as we can observe here 1346.09. so as we can observe here that as we can observe 1346, so analytical results are 100% correct and okay. So just copy it here and paste it here. So this is the velocity of the slider VB or d dot, because d dot actually is the first derivative of the position, which is actually the velocity. So in this way open circuit has been calculated. So right circuit velocity, graphical and trigonometric result has been completed. And again sorry for being this video lengthy, so I hope you will be tolerating, and jazakallah and assalamu alaikum. For the second or the left circuit, I will be recording the video shortly for your benefit. Or assalamu alaikum.